Hello, I'm Krista Tweed, an applications engineer with HBK. In this video, I'm going to explain how torque and speed measurements are made using the eDrive power analyzer and an HBK torque transducer. Users testing electric motors are typically interested in understanding torque in a variety of ways. When calculating efficiency, the parameters used to make the efficiency calculation, input power and output power, should be calculated over the same time period. Therefore, mechanical power and electrical power should be synchronous, calculated over the same time period. In perception, that is done by calculating both quantities using the same cycle master. However, there are many interesting things happening with torque that occur on a much faster time scale than the electrical cycle. For that reason, perception also provides more dynamic torque measurements through the instantaneous torque and raw torque signals. HBK recommends using the frequency output of a torque sensor to get the most accurate torque measurement with ePower. HBK's torque transducers are sold with a specified center frequency. As an example, consider the T40B 200 Nm 60 kHz transducer. The frequency of the digital output varies with torque. At zero torque, the output is the specified center frequency, in this case 60 kHz. Across the full range of the torque transducer, from maximum negative torque to maximum positive torque, the variation in frequency is equal to the center frequency. So for the example transducer, the frequency at minus 200 Nm is 30 kHz, zero torque is 60 kHz, and 200 Nm is a 90 kHz output pulse train. The power analyzer's timer counter channel calculates the frequency of the input signal over a user-specified measuring time. The measured frequency is converted to torque using the linear relationship appropriate for the sensor. Thus, the timer counter channel calculates a new torque value for each measuring time interval. I want to be sure it is clear that the measuring time for the timer counter channel, which is sometimes referred to as the update rate, is a separate entity from the sample rate for the recording. The sample rate set by the user may be faster or slower than the measuring time. If the sample rate is faster than the measuring time interval, the timer counter waveform will have consecutive samples with the same torque value. If the sample rate is slower than the measuring time interval, the recorded data will not include every unique torque value. The sample rate for the recording is set in the acquisition control panel or the acquisition page of the settings sheet. In contrast, the measuring time is set in the setup panel for the motor component in ePower. To determine the appropriate measuring time selection, the user needs to consider two variables: the period of the slowest measured frequency and the required accuracy of the measurement. The torque sensor will output the slowest frequency when it is measuring maximum negative torque. For our example transducer, the lowest frequency is 30 kHz, which corresponds to a period of approximately 33 microseconds. In order to measure at least one period in every measuring time window, the measuring time must be at least 50 microseconds. The required accuracy of the measurement must also be considered. Timer accuracy is a trade-off between update rate and the minimum required accuracy. Accuracy increases as the measurement time increases. However, the update rate decreases as the measuring time increases, since the timer counter channel provides one torque result per measuring time. Thus, you get a less dynamic result as you increase the accuracy of the measurement. The data sheets of the GenDAC input modules have a table that specifies the maximum timer inaccuracy as a function of signal frequency and measurement time. You can download the GN310B power module datasheet using the link shown here and see the full table with that information. These example graphs are taken from the datasheet. HBK's eDrive power analyzer provides 3 different torque signals for the user as real-time formula database results. The name of the signals are motor.out.mraw, motor.out.minst, and motor.out.m. All can be found in the real-time formulas motor group in data sources. Motor.out.mraw is the direct output of the timer counter channel. The update rate of this signal is the measuring time for the timer counter channel. This is the proper signal to use for torque ripple investigations. Motor.out.minst is called the instantaneous or dynamic torque result in ePower. This signal averages mraw over the user-specified dynamic averaging time. The default setting for the dynamic averaging time is 1 milliseconds. However, beginning with Perception version 8.3, the user can set that dynamic averaging time to a different value in the generic settings dialog in ePower. Motor.out.m is torque measured using the cycle detector settings of the motor component in ePower. Many users link the motor cycle detect to the inverter to make sure both mechanical and electrical power are calculated over the same time to provide an accurate efficiency result. However, there are 2 other options available. You can select the reference or Z-pulse of the torque transducer's speed system to set the cycle measurement time. You can also use a fixed time as a cycle. Viewing the 3 torque signals simultaneously can help users understand each of the signals. The display shows mraw in the top pane from a test where the measuring time was 500 microseconds. A time marker was added to the display to show the update rate for each signal. The second pane shows minst, which had an update rate of 10 milliseconds in this test. Pane 3 shows M when the torque cycle detect was linked to the inverter. The final pane shows phase 1 of the current signal, labeled I1, it's the red trace, and the cycle master white square wave. The inverter cycle detect was configured to use 10 cycles of the current as the calculation period. You can clearly see that the calculation intervals for M line up with the cycle master. A similar approach is taken with the speed signals in Perception ePower, resulting in 3 variables related to speed. Motor.out Y mechanical shows the motor angle. This is the direct output of the speed timer counter channel. Motor.out.ninst is the dynamic or instantaneous speed measurement, calculated using the same dynamic update rate as the instantaneous torque. Motor.out.n is the speed measurement using the cycle detector settings of the motor component in ePower. This display shows the 3 speed signals. Mechanical angle is in the top pane, cycling between 0 and 360 degrees. Instantaneous speed is in the second pane with an update rate of 10 milliseconds. Speed measured over the inverter cycle master is in pane 3. Phase 1 of inverter current and the inverter cycle master are shown in pane 4. In addition to the output of the timer counter channels, the eDrive power analyzer also records and gives you access to the torque and speed input signals those raw pulse trains that are going into the timer counter channels. If you are not seeing the torque and speed values you expect from the power analyzer, reviewing the input signal pulse trains is a good place to start. You can find those raw signals in data sources in the same motor.out group. Torque_raw is the torque channel pulse train. The ABZ signals from the encoder are RPM-A, RPM-B, and RPM-ref. Digital inputs are displayed in perception as high, thick line, and low, thin line traces, a bit different than the analog channels or timer counter signals. The A and B traces from the encoder should be offset by 90 degrees, as you can see in this example. If the encoder has a reference pulse, you should see 1 pulse per revolution. The torque raw pulse train should show relatively even pulses. In summary, the eDrive power analyzer provides users with multiple torque and speed signals measured over different time intervals. The user is able to get accurate efficiency calculations and study dynamic behavior such as torque ripple with a single test. Thanks for watching. If you have questions on perception or any other HBK product, please feel free to contact technical support via email or the HBK website. Our website includes local contact information for our worldwide offices, including phone numbers.